Perfect. And now I need to share my screen. Just a moment. Okay. So in the last class, we talk about some of the reference soil groups, and we start to talk about the histosols. And just to check, just remember, histosols are those organic soils, those soils that possess a folic or histec horizon, thick folic or histec horizon. Okay, and these soils can be found in several places, like flooded sites, cold areas in high mountains and highlands, and from several mechanisms that could improve and favor the concentration, the accumulation of organic carbon, the organic matter. Okay, and this soil group should be one of the first that you think when you are in the field and you start to describe and trying to classify on soil, because if it possess these organic horizons, the folic or histec horizon, and follow all the criteria to be classified as histosol, it's histosol. You just don't need to think other reference soil group. Okay, so we always need to check if we have organic diagnostic horizon, and if we have this organic diagnostic horizon, if it follow the thickness and all the criteria to be classified as a histosol, you are in a good way to classify it as a histosol. We also saw the anthrosols and technosols, and they both are related to soils produced or deeply mixed by men. And they could be associated with several horizons, several surface diagonal horizons that can be found in surface, and they have specific soil properties that indicate, that evidence this human activity. They can be the Arctic, hydric, pelagic, pteric, anthratic, pratic, any kind of this surface diagnostic horizon could be related to the anthrosols. Like in this picture, we can see the pratic horizon, and here we also can see the pratic horizon, but they are related for to several diagnostics horizons, and they are usually related to ancient human occupancy. Okay, so you just need to think with anthrosols when you are talking about soils that are deeply mixed by men in the past. And we have the technosols, those soils that produce it by modern societies that are related to modern human activities and produce several soil properties that express this process. Okay, so the first one is for those soils that possess thick organic layers, thick organic horizons. And anthrosols and technosols are related to deeply influenced soils, soils that are deeply mixed by man, produced by man. Okay? And let's talk about the cryosols. The cryosols possess a specific occurrence. They are quite related to periglacial areas in North and South. We can see them in Africa, or we can easily see them in the South America. We only can see this in some countries like Russia, Chile, Argentina, Canada, United States, and of course, Arctic and Antarctica lands. So it's not so common, but it possesses specific soil properties that are related to influence of ice and influence of freezing and thawing of water. Okay, the cryosols, it possesses a cryotic horizon, and the cryotic horizon is a diagnostic horizon that it's related to a specific temperature. It's a specific property that we don't usually think when we are talking about other diagnostic horizons. That is the temperature horizon should possess temperatures below 0 Celsius degree for at least 2 consecutive years. So you should monitor the temperature of this horizon to identify the permafrost, a frozen layer of soil that composes the cryotic horizon. So you only can find the cryotic horizon in very low temperatures. And why it's so important, the very low temperature? Because it's freeze soil and freeze water, and above the permafrost, the frozen layer, we have the active layer, and the active layer, it's frozen and unfrozen according to the season of the year. So in the summer, when water is liquid, water could migrate from the top, from the bottom of the active layer, and this kind of migration could carry clay and could move also coarse materials like sand and gravels. So the cryotic horizon, it's quite related to low temperatures and low activity and low migration of materials, but it's quite common that above the cryotic horizon, we have a lot of things going on. We have a lot of process of migration, transformation, weathering, leaching, because we have liquid water for at least one season. This water can be related to unfrozen the thawing of the soil, of this surface layer, but it also could be related to the thawing of snow, ice, and other areas. And today we also stood the mixing of this active layer, because the degradation of permafrost, the degradation of cryotic horizon. In this picture, you can easily see here the cryotic horizon. Below this tape, we can see here ice frozen all soil, but the cryotic horizon is above this layer, because also here in 4 centimeters, we also can find low temperatures. And as I said, the cryotic horizon is related with low temperatures. It's not for other specific morphologies, but specifically to low temperatures. And of course, we have other morphological features that express this low temperature. I can show you some of them here. Like in this picture, this is a sample of soil that we took for micromorphological analysis, and everyone can easily see a very dark color here, a red and dark color, and here we can see a light yellow color, and we can easily see a lot of gravels of coarse material, and here we see less lower quantity of this coarse material. We also have gravels. We also have these coarse fragments, but its content is lower. So here we have a different color, a different texture. We have more fine material, more clay, and here we have a lighter color and more gravels. This difference of color evidence the cryoturbation. And what is the cryoturbation? Is the turbation is the mixing of soil because or due the difference of potential, difference of temperature. In the summer, the soil, the surface of the soil, it's hotter than the subsoil. So because we have a difference of potential, we have a difference of temperature, water from the subsoil, from the bottom of the active layer and the top of the cryotic horizon, in the top of the permafrost, migrate from the subsurface of soil to the surface. And this migration also brings clay. And this migration, you can see here in this plume of clay, in this plume of fine particles. And here we don't have this migration. So this different color evidence the migration of fine particles from the subsurface to the surface. Okay, so this is one of the morphological evidences of the cryotic horizon of the permafrost. But it's not so easy because we can see this morphological property also in soils that in the past was frozen. In the past, we could see a cryotic horizon, but the permafrost or the temperature is too high to identify the permafrost today. So if you look for some hot areas in Canada or areas in United States that's not so cold, you can see some soils with this evidence of cryoturbation, but you can't see permafrost there anymore. You can't see low temperatures there anymore, but they are relict of colder past climate conditions. Okay, so it's why we like to use the temperature as the best morphological evidence of the cryotic horizon. Here, in this picture, we can see this block, this line, this plume of clay here. You can see here a dark green color with a different texture of this area. You can see here a wave boundary, a wave transition between this horizon and this horizon. And this green clay material, it's upwarding, it's migrating from the subsurface to the surface because we have a difference of temperature, okay? Oh, we also can see in some cryosols some dots, some spots of organic material, this dark spots here, and they are related also to my cryoturbation because the cryoturbation also makes the soil from the surface to the subsurface because the process of thawing and freezing of soils creates some cracks in like vertisols and soils that we have high activity clays. These cracks could be very large and sometimes some material in the surface could migrate or can be eroded and could follow inside these cracks, and after that could be mixed with the soil. So we can easily see dark spots inside a subsurface horizon because the cryoturbation and the mixing of soil. all of these morphological evidences induce or help us to identify the cryotic horizon, okay? And the cryotic horizon should be identified in the first 100 centimeters from the soil surface. So we should identify this low temperature in 100 of soil surface, or we could find these low temperatures inside 200 of centimeters from the soil surface if we find this cryogenic alteration, this evidence, this morphological evidence of cryoturbation. Like I said, the cryoturbation, the mixing of soil, some frost halves inside the soil, cryogenic cryogenic sorting. I will show you a very good image for that. But cryogenic sorting, you can see here too that it's the selection of material by ice, by the thawing and freezing, but especially the freezing of soil that select for fine particles and create boundaries between the coarse materials, the coarse textures, and these fine materials. Okay? We also can see some thermal cracking, some crackings in the soil because during the freezing, we also can see the ice segregation like this. We also can see the ice formation inside the soil like a layer. You should remember the WRB and the soil taxonomy, they use a layer, specific layer to ice segregation. And we also can see a partner ground in areas that we can see the cryosols. Let me show you a picture, a very good picture. This is the partner grounds. You can see an instrument here, so they are very large, and you can easily see a partner in the surface. It's because we call them partner grounds, and they are related to cryoturbation and cryogenic selection of particles. So the coarse materials, they concentrate in the borders of the circles or polygons, and the fine materials, they concentrate inside or into in the middle of these circles. It's quite common to find this in areas that we can find the cryosols. Even in Mars, we can see this partner ground, and it's what we know that we have water in Mars, at least in the past, okay? Because we can see there some partner grounds too. And beyond the cryosols, we also can find leptosols that also are soils that are not so evolved, so sorry, because there in the cryosols would have climate conditions that did not favor the leaching and the weathering of the primary minerals. So it's quite common that cryosols are eutrophic, or they possess a high base saturation, and they possess a lot of primary minerals because the parent material tends to be not so or deeply leached or weathered because we have specific climate conditions. So we have a lot of physical weathering, and this physical weathering only destroy the material, the coarse fragments, and produce finer materials. And the low weathering, they produce clay, okay? So the material is not so weathered or not so weathered, not so developed. We don't see high developed horizons with strong grades because we have climate specific conditions. But We also have the leptosols that are related to low developed soils, soils that are not so thick, but here the temperature is not specific property, specific soil formation factor that affects the soil property. The leptosols could be found around the world. We can see in Andes, we can see them in Himalayas, we can see them in every highland and every mountain that you can think, because there it's a lot, they have a lot of erosion, and erosion always keep the soil very, very thick. Okay, so climate conditions could favor the formation of a soil that's not so thick, but it's not a low temperature. It's other soil formation factors that allow the formation of a weak developed soil, a soil with a weak grade. Relief, it's quite important, because if the slope is very high, if you have a lot of erosion, all the soil, it's continuous, always being eroded, so you can't form strong grade or even moderate grade. You can find a lot of fine particles, of a lot of fine materials, because soils and this less dense materials are always being eroded by wind, water, or other geomorphological agent. Okay, so the leptosoils are those weak developed soils that could be related to relief, because the erosion, they could be related to the specific parent material that could be very hard to be wafered. Some granites, for example, or some quartzites, for example, they possess a lot of materials that's quite resistant, I'm sorry, to weathering. So you can easily find some leptosols in areas that we found quartzites, because that's a lot of quartz, and so this mineral is not so easily wafered, and so we don't can create a clayey horizon or a clayey soil with a strong grade. And of course, some of these areas that possess this kind of parent material also possess a sloped area, also possess a slope that's very high, and they always are being eroded. Okay, and the leptosols, it's quite important to understand something, that they are those soils that you can find a continuous rock starting at 25 centimeters from the soil surface. So if you can find rock starting at 10 centimeters or 5 centimeters or 20 centimeters or at least 25 centimeters, it's already a leptosol. Okay, so you just need to think, okay, this soil, it's so shallow, that's call it a leptosol, because the continuous rock, it's very, very close to the surface. Or we can find some soils that possess a high volume of coarse materials and less than 20% of fine earth. What is fine earth? Sand, silt, and clay. And of course, here we include that plant residues or organic materials. Okay, so in this specific case, in this picture, we can see rocks only here, the rock here, but we can see a very low quantity of fine materials, and we can see easily broad and coarse materials in all this horizon. So it's because this picture is a picture of a leptosol, because even with the rock, it's below 25 centimeters of depth, we can see coarse material in a high quantity, in a high amount in this horizon. Okay, and of course we cannot see a derrick or petrocalcic or petroduric or other horizons that are related to specific soil properties or specific soil process and so on. So the leptosols are those soils that did not possess thickness, a high thickness. They are not so thick, and they are related to only this low weather condition. They did not register, we don't see any evidence of other soil process, other so specific soil process to create the soil. So it's a shallow soil and just that. Okay. Here we can see a leptosol. It has only 20 centimeters, so the rock can be seen below 20 centimeters. Okay, we can see it here and here, so it's very, very shallow. And in this case, this leptosol is related to parent material that's it's quite hard to weather. This granite, it's quite hard to weather, and it's because we can see this soil that's very, very shallow. Okay. We also can see the solonets, and the solonets, they are related to a natric horizon. They are related to a natric horizon. The natric horizon, it's related to for those soils that possess a high quantity, a high amount of sodium. And the natric horizon should start at least 100 of centimeters from the soil surface, from the mineral soil surface, I'm sorry. So if you have a histic or photic horizon, you don't need to count them. But from the mineral soil surface, from the first A horizon, you start to count, and inside into this 100 centimeters, you find the natric horizon. And the natric horizon are those horizons that are related to a high amount of exchangeable sodium, okay, in the cationic exchange capacity. So the IPS, it's higher, it's equal or higher than, it's not I, I'm sorry, it's EPS, it's equal or higher than 15%. So you can find in the natric horizon a high percentage of the CEC that's fulfilled by sodium. And the natric horizon, it's also related to an increase in the clay content, a significant increase of clay content in the subsurface horizon. So the natric horizon is that horizon that possesses a higher amount of clay in the subsurface or higher than the surface or the overlaying horizon, and it's related to a high quantity of sodium. The natric horizon did possess these properties because these characteristics, these properties, because this high quantity of this high amount of sodium is an evidence of clay migration, of the genesis of the clay migration. If you remember in the past, we said that sodium helps the disaggregation, the destruction of beds, of aggregates, because sodium has a low affinity with clays and has a high ionic radius. So the clays are not so close when they absorb sodium, And because of that, you start to destroy some aggregates, some pads. And because of that, we have the migration of clay from the surface to the subsurface horizon. Okay, because all pads in the surface horizon, they are destroyed by a high quantity of sodium. They are chemical dispersed by sodium, and are not so easy to find soils that possess the natric horizon, because natric horizon is related to a high percentage of exchangeable sodium, and sodium it's easily leached in tropical and wet air in wet tropical climates, in areas that the rainfall is higher than the evapotranspiration. But in arid and semi-arid regions, in arid and semi-arid sites, we have evapotranspiration higher than the rainfall, higher than the precipitation. And because of that, we have the concentration of salts and especially sodium in the soil. And if you concentrate sodium in a high quantity, in a quantity that allows this destruction of aggregates, you also favor, after that, the migration of clay. And the migration of clay during the rainfall will bring the clay from the surface to the subsurface. So you create a subsurface horizon that concentrate clays that were migrate from the surface horizon or the overlaying horizon, okay, and also concentrate this high exchangeable sodium percentage, because sodium also are leached from here and concentrate here. So we have a soil that possess here a high pH, a high content of exchangeable sodium, and a high content of clay. And here we have a horizon, a layer that possess acidic pH, low quantity of clay, low quantity of fine particles, only sand and silt are relevant, and they possess lighter colors, because organic matter, organic carbon also could migrate with the mineral clay. You can easily see that here in this horizon, we have this columnar structure. The natric horizon is quite related to columnar and prismatic structures, okay? Because the shrinking and swelling of these clays that produce this vertical elongated structures. And we also can see a darker color than even here, a darker color than the surface horizon, because the organic matter also migrate, and now they create this dark color in the subsurface horizon. Okay, so the natric horizon, it's quite related to arid and semi-arid regions or sites, because they are related to a higher evapotranspiration, or at least a high evapotranspiration than the precipitation. And this arid or semi-arid condition favor the concentration of salt. They are not leached, and the high concentration of sodium destroy the aggregates and induce the migration of clay from the surface to the subsurface horizon. Okay? The vertisols are also related to semi-arid and arid regions, or they are related to a modern exposed lands. So if you can see a lagoon or a land very close to the sea that in the past was flooded and today it's above the sea level, or it's not flooded anymore, you can find some vertisols there. The vertisols, they are related to the presence of the vertical horizon inside the first 100 centimeters from the mineral soil surface. And the vertical horizon, it's those horizons that you can find this large cracks. The vertical horizon is a clayey horizon that possess a high quantity, a high amount of expensive clays that could shrink and shrivel easily due to variation of soil moisture. So the vertical horizon, it's related to specific conditions, conditions that express low weathering or a recent explosion of the parent material, because they are related to a low weathering materials that possess 2 to 1 clays, high activity clays. And these high activity clays, they should very abundant in this horizon. They should be very easy to find there. Okay. The vertical horizon, although this dark color did not possess a high quantity, a high amount of soil organic matter or organic carbon, okay, this dark color is related to the compression of the stress of organic residues, because these cracks, like in the cryosols, could favor the migration or the falling of this surface horizon. So some organic residues or organic layer, or even some pieces, some aggregates of this organic horizon could follow inside the crack. And because of the shrinking and swelling of this material in the subsurface, we are compressing and stressing this organic material that brings this dark color. And the other minerals that we can easily find at the vertical horizon, they did not have any kind of color. They are white. So we are only mixing dark materials with white, and we have this dark color. So they are not an organic horizon or possess organic layers or have a low density. They possess a high density, okay, in opposition of that. They have a high density because we have a clay material with high activity clays, okay? So the vertisols should possess the vertical horizon. Is that this horizon that I said that possess a lot of evidence of material that it's a high activity clays, like these large cracks that are shrink and shrivel cracks, okay, that are a high quantity, a high amount of clay, at least 30% of clay, and it could possess any morphological evidence of clay stress, of pedal features or feature or stress features that evidence this shrinking and swelling process. Okay. The vertical horizon, you just need to remember that possess at least 30% of clay, but it should not possess a significant higher quantity of clay in the subsurface. So the quantity of clay in the surface horizon and the subsurface horizon should be very close. Okay, it's not like the other soils, the soil reference soil groups that we call that possess a significant clay increase. Okay, so it's just the same material, but we have this shrinking and shredding process that create some stress features and shrinking, shredding cracks and some shiny surfaces that are related with this high activity clays. We usually found them in areas that possess a arid and arid climate because they are soils that are not so weathered. If the weathering it's very high, like in the moist and hottest areas in the South Africa or Africa, it's quite hard to find the vertisols there because these climate conditions induce a deeply and intense watering and leaching and the destruction of these high activity clays. Here we can see other picture and we can see this dark color, but did not think that the organic carbon is high. As I said, it's just a mixing of organic carbon that possess this dark color and a lot of minerals that did not have any specific color. So all the soil is dark, but the organic carbon content is very low. We also can found the soil chunks, and the soil chunks, they're related to the presence of the salic horizon. And the salic horizon, if you remember, could be a surface or a subsurface diagnostic horizon. So we can find them in any part of the soil, in depth of the soil, and the salic horizon are related to the concentration of salts in the surface or in the subsurface. Okay, so the soil chocks, they express the concentration of salts in semi-arid or arid regions in sites that evapotranspiration is higher than the precipitation, higher than the rainfall. In opposition of the solonets, the solid chunks, they have the concentration of other salts are not specifically sodium, but we can see here calcium sulfate, sodium chloride, and other salts that it's not specifically abundant in sodium. We can see several or very high difference of minerals that can found here. Potassium chloride and calcium sulfide are the most abundant. They are the most common minerals that we can found in solid chunks, but we also can see some salts that are rich in sodium, but the exchangeable sodium percentage is not high in this case. Okay, the electric conductivity, that's high because we have a high salt content. We have a salic horizon. Okay, so the soil chunks are those soils that have the salic horizon start in the first 50 centimeters from the soil surface, and they did not have a tonic horizon. If you don't remember what is a tonic horizon, it's those horizons that possess a high quantity of sulfate and sulfite. They are related to those soils that are formed in tidal areas, okay? And they are not permanently submerged by water. So it's not permanently flooded, okay, or influenced by tidal water, okay. These soils are generally related, also they are generally related to semi-arid and arid regions. And they differ from the solonets because they have a concentration of several salts. We usually can see solonets that evolve from a solo chunk. When a solo chunk exposed to a high rainfall regime, to a high precipitation conditions, these salts are fastly leached, and in some cases you can see just a high concentration of sodium. So this past solo chunk turns into solonets. Okay, so the solo chunks, they are specifically to drier conditions, to the driest climate conditions that you can think. And the solonets are those milder conditions that, of course, it's a dry climate, but it's not so dry like the solo chunks. So these orders are quite related to the leaching, and because of that, are quite related to the climate conditions. Here we can see some salt precipitations in the subsurface, and in the last picture we could see this in the surface. We also have the glacial soil group. This reference soil group is specifically related to glacial properties. So it's specifically related to this gray or blue color that we can see, and that's produced by the flooding of the side, the flooding of the area. So glacials are those soils that are permanently or seasonally flooded. They are significantly influenced by water, by groundwater, especially from the water table or groundwater. Okay, so the glacials, they possess clay properties in a 25 centimeters thick layer, and this layer with clay properties should start at least 40 in the first 40 centimeters. So we start to see this gray color like in 20 centimeters, but in a very easy way, 30 centimeters. So it's a glacial, okay? And of course, this blue color has much more than 25 centimeters thick. So, okay, it's horizon with clay properties and possess some reducing conditions in some parts of every sublayer. So each sublayer should possess any kind of reducing conditions. And these reducing conditions could be, for example, reducing morphic features like models, plintite, masses, concretions, any kind of evidence of variation of reducing conditions of EH. If you have any kind of glacial property or models or iron and manganese masses, concretions, nodules, they express the variation, the oscillation of EH, and so brings the soil to be classified as a glacial. Okay? If they possess a molic or umbric horizon, this surface horizon should have less than 40 centimeters thickness, because if they have 40 or more centimeters, they should be have classified as other reference soil groups, like the molly soils and umbri soils. We say about them in the next slides, okay? And if they have one of these conditions, if they are directly underneath the molic horizon, this layer should possess less than 10 centimeters, and the lower limit should be equal or higher than 65 centimeters. Okay. If we have permanent saturation by water, like a water spring or the water table, it should start in the first 14 centimeters in the mineral soil surface. So if we have any kind of water layer, the double V layer, the Y layer, we can find the soil as a clay soil. We can classify the soil as a clay soil because the WV layer, okay? Here we can see this gray color, easily can see this gray color, okay? And it's quite funny because in the surface we have this light color that show us concentration and precipitation of salts, like in the salt chunks, but the thickness of this horizon is not so thick to be classified as a salt chunk, so it's classified as clay salt. And this kind of clay salt is related to semi-arid and arid regions, because in some areas, even in arid and semi-arid regions, we have the concentration of water in some areas and the migration or the oscillation of the water table, and even in semi-arid or arid sites, we also could produce glade droplets, reducing morphic features, and so we could produce clay salts. Here we can see,
JJ, JJ,
yes, yes. Mhm.
I've got a question on this one. I have experienced this in one of the fields, farmer's field. So there was, it has some contours. I think there were three, if not four. So on the first contour, this was the case. But as you move down, that contour was the first one. And as you move down the slope, it was a different case. The soil was different from this one. So
Okay,
I'm
okay,
asking what could be, what could have attributed to that, to the change in the profile as you move down the slope, where you have water closer to the surface on the upper contour compared to the
okay.
lower ones.
Mhm. Which morphological property you can see this difference? It's just a difference of color, and this subsurface material is darker. Which morphological property changed in the soil profile that you are describing?
Yes, for the first contour, it was exactly this color. It was darker on the top surface layer, but as you move
Hmm?
down, it was grayish. And on the last contour, he actually experienced that during plowing.
Mhm.
But on the last contour, the tractor was able to plow, but it
Okay,
couldn't
okay,
plow on the first contour, and it was dry. It was during the dry season. I think we experienced the rains like a month before the planting. But
okay, okay.
on the towards the lower side of the slope, the soil was darker. It was brownish. throughout, even though we didn't dig the profile down there, but it was
Oh,
brownish.
okay, okay. Maybe, maybe, okay. The soil
Mm-hmm.
that you are describing is not specifically a clay soil. Maybe it could be a stagnosol that we are discuss in the next slide, because some soils, they have this oscillation of EH, because the oscillation of the groundwater, the water table, that produce gray colors in the subsurface, and all the subsurface horizons, they possess this gray color, and in the surface we have this dark colors, okay. And in
Mm-hmm.
the case of stagnosols, you have a dark color in the topsoil, in the surface. You see gray colors in the middle of the soil, for example. And after that, we see a dry state. We have yellow or even a dark color. We have stronger colors. We have a high chroma. And the stagnosols are different from the clay soils, because the stagnosols, we have some cemented or some low pores layer that avoid the migration of water, so
Mm-hmm.
create saturated horizon close to the surface or in the middle of the soil. And there we can see these gray colors, but below the cemented layer or this low pores layer, we can't see these gray colors. We see again high chroma. I will show a
Mm-hmm.
picture of stagnosols, and maybe you will check, okay, maybe it's not a stagnosol or it's not a glacial, but probably it's a stagnosol. And it's, as I said, this difference of morphology, this difference of color, and the other soil properties are related to the direction of the water. If the water comes from the bottom of the soil profile and migrates from the subsurface to the surface, is the migration of the groundwater, is the migration of the water table, you create a clay soil, because water
Mm-hmm.
brings or comes from the subsurface. If you have the rainfall and a low conductivity, a low permeability of this water that's came from the rain, because you have a cemented layer, you have a rock layer, or have a low spores layer that avoid the migration of water. You did not have a glacial. You should classify it as a stagnosol. Okay, is other reference soil group, because the direction of the water is from the up to the bottom, and the glaison is from the bottom to the top soil. Okay,
Okay. Okay.
okay,
Thank
okay.
you.
When we
Yes.
well, welcome, welcome.
Thank.
Well, when we start to talk about stagnosols, maybe we can come back from this question and check which soil you think that could be more adequate for this case, for your specific case. Okay,
Okay. Thank you.
welcome, welcome. Okay, in this case we can see a darker color, okay, but here a dark material, a gray and dark gray material with some yellow zones, and these yellow areas, they are related to iron and some sulfates that could be produced, could be precipitated in the cracks, because here, of course, we have oxygen. So we produce some oxymorphic features in the clay soils that express this oscillation of pH, because the oscillation of the groundwater, the water table. Okay. We also have the endosols and the endsols. They are related to endic or vitric properties. And the endic or vitric properties, they are not so common in tropical areas, especially in wet tropical areas, because they are they have a high quantity of elephants, immogolite, and very easily weffered minerals that are produced by the recent modern crystallization of magma in areas that we have volcanic activity. So it's quite common to find in Hawaii and Japan, but of course we can see this in Brazil. We can see this very easily in Africa. We usually see this kind of soils in Asia, because there we have intense volcanic activity in large areas, and so we produce rocks that are very, very rich in mogolite and allophane, and these soils are the endosols. These endosols are soils that possess a high affinity with water, and they are mineral soils, but they possess a low density. So different from the other soils that we are talking about, you can see this yellow color or some these red regions, and you already think, okay, this could be iron oxide, this could be hematite or goethite. No, it's not. It's not hematite or it's not goethite. It's just mogolite and aliphanes, low crystallinity minerals that they present this color, and these low crystallinity minerals, they are very, very light. So the soil, it's very light. They possess a low density. It possesses a high porosity, and they possess a high affinity with some anions like phosphorus. Okay, so the endosols, they are soils that can be easily classified if you have data about minerals and the chemical reactions that affect the soil. But in the field, you need to consider some context, like, okay, what is the parent material of the soil, where I'm digging the soil, and how dense is the material. Okay, the density is very high, so the density of the particles is very high. Okay, it's not an andosol. If the part densities of the particle density is very light, okay, maybe it could be an andosol. Okay, so you should find andosols. You will find andosols in areas that you have a high volcanic activity, and these soils are related to a low density, a high affinity with water, and a high affinity with anions, especially phosphorus. Okay. Oh, I'm sorry. We also have the podzol, and to me, the podzol are one of the best soils because I think that they are very beautiful. The variation of color because the production of this spotted horizon in the soil, it's amazing. As you can see, this dark horizon here is an A horizon, and here we have this light color, this white color is an E horizon, and here we have a dark horizon, and here the darkest horizon in this picture. And this and these horizons, they both are spotted horizons. If you don't remember what is a spotted horizon, the spotted horizon is related to horizons that concentrate organic carbon, soil organic matter, and or aluminum and iron oxides that migrate from the surface to the subsurface horizon. The migration of organic matter and or aluminum and iron oxides, it's called podzolization, and it's why we call the soils as podzols. Okay, these podzols are quite related to sandy materials, as we can see in this picture, because sand materials couldn't preserve organic matter in the surface. So if we have a wet climate with a high precipitation and we have a sandy material, a sandy texture soil, the migration of water through the soil profile will bring the material from the surface and concentrate it in the subsurface horizon. Okay, and as I said in the past, this spotted horizon mark a level of the water table in the past. So if I collect a sample here and date this material, this organic carbon, I will date the position of the water table in the past. Okay, so it's why I think that this soil is very important, because it could also bring us an information about the evolution of the landscape very easily, very, very easily. Okay, so again, the podsoils are those soils that possess the spotted horizon in the first 200 centimeters from the mineral soil surface, and the podsoils possess this spotted horizon. The spotted horizon is those horizons that concentrate soil organic matter or and are aluminum and iron oxides in the subsurface, because we have a wet climate and sandy texture. This reference soil group, it's quite common in Brazil. We have the second largest um, second largest how can I say this in English? I'm sorry. The second largest mapped fragment of podzols in the world, in Amazon rainforest. And it's quite easy to understand why, because a lot of soils that evolve in Amazon rainforest evolve from the weathering of sandstones. So of course, the soil could be sandy, and we have a wet tropical climate. So we have a sandy soil with a lot of rainfall that could migrate organic matter that produced in the surface by the vegetation and animals in the surface, but migrate and get the subsurface this dark color. This is not an A horizon, this is a B horizon, is a spotted horizon. A horizon could concentrate organic matter and or aluminum and iron oxides. Like in this picture, we can easily see the A horizon, the E horizon with this white color, this light color, and here we have a dark color which concentrates soil organic matter and iron. And here we can see this yellow and light yellow color, which register the concentration of only or at least more iron oxides than organic matter, and the color is just yellow. Okay, so the iron oxides here and here, the organic matter, they did not are formed here. They migrate from the E horizon and from this A horizon. The podzols are also very common and very famous in coniferous forests. Okay, here it's other picture, and here we can see a dark color and a lot of gravels of iron, some yellow and red gravels that express the migration of iron oxides. And talking about iron, we could talk about plantosols. The plantosols are soils that have a plantic or pisoplantic or a petroplantic horizon in the first 100 centimeters from the mineral soil surface. If you don't remember what is a plantic or pisoplantic or a petroplantic horizon, we will see in this slide. Here we have the plantic horizon, and the plantic horizon, that horizon that possess a high percentage of area covered by iron masses, iron and or manganese masses, or metals, or plantite, or concretions. Okay, but the content of concretions should be very low, and the content of iron masses, iron manganese masses, or plantite should be equal or higher than 15% per area. Okay, so in this case, we have a soil that possess a lot of oxymorphic features in the subsurface, and this morphological feature is related to the oscillation of the groundwater and the dominance of oxidation conditions of oxic conditions. So in this case, in the past, this soil was very close to a clay soil with gray colors, but the oscillation of the groundwater did not course anymore. So the groundwater is very there, very dead, is a very deep layer. And now this ancient gray color, this ancient gray horizon gets red because the oxidation of iron 2 to iron 3, which produces iron masses, iron concretions, and iron nodules and plantites. So the plintosols are soils that was influenced by the water, by the groundwater table in the past, by the water table in the past, but now they are not flooded, or at least the water table is not so close to the surface. Okay, here we can see the pisoplantic horizon that's related to a high quantity of gravels that is composed by iron concretions. And here we can see the petroplantic horizon that it's composed essentially by iron concretions and nodules that are cemented, and they come into a specific layer. They create a continuous layer, a cemented layer, and here we call a plintosol with a petroplantic horizon, a horizon produced by an intense oxidation of iron and cementation of materials. So all of these three conditions, the plantec horizon, the pisoplantec horizon, and the petroplantec horizon, they all they all create plantosols, okay? Because they evidence the oxidation, cementation, concentration of iron in dots or spots. The difference is only that here we have a low concentration and here we have the highest concentration and cementation of soil by iron. We also have the planosols. The planosols are those soils that register stagnant properties because we have a high or significant difference of texture. So in this case, it's quite easy to understand that here we have a high difference of texture. Here we have, you can feel the texture of this picture, a sandy texture here, and here a clay texture. And because of the difference of texture, the water can't migrate very easily inside this horizon, and because of that we have some stagnant properties or reducimorphic features, okay? And because of that we have the planosols. So the planosols are the soils that we have a significant variation of clay content between horizons. And because of this high variation of texture that we call abrupt textural difference, this high variation induces stagnant properties or reducimorphic features in the soil. And in this picture, we can see here this gray colors, and here we can see some models of iron and or manganese because this low porosity of soil, okay? Planosols are soils that have two specific morphological conditions. It possesses a high variation of clay content and some evidence of this high, how this high variation of clay content induce water to be migrated from the soil. How this high variation of clay content could reduce water migration, water conductivity into or through the soil profile. And here we have the stagnosols. The stagnosols are very close to the planosols, but the difference is that here we did not see this difference of texture. Here we have other soil property that induce a low migration of water. And so we have, in this case, a thick organic horizon or even an A horizon, a very dark horizon. And here we can see this gray color. And here we have this yellow or red color because this subsurface horizon, it's low porosity. The low porosity induce a low migration of water. So the water starts to stagnate here, and this stagnant water produce stagnant properties that are these gray colors produced by low migration, low conductivity of the soil. So the stagnant soils are those soils that possess problem to conductivity of water through the soil, and this problem, this low permeability of soil, is not exclusively related to a difference of clay content. It's different from planosols. Okay, so the stagnosols could be because here we have a sea horizon, or we have a layer of rock, or we have some coarse fragments here, or we have a cemented material here. Um, any kind of property that you can think that avoid or reduce permeability, the conductivity of water, and because of that we create a horizon with stagnant properties, with gray colors. It's quite different from the glacials because, as I said, the glacials, you will see always a gray color very close to the bottom, and you can see, not so easily, but sometimes you can see this red or yellow colors close to the surface because the water table did not achieve this soil surface. So their horizons, those horizons that are not affected by the water table, are red or yellow. But here in the stagnosol, you can see these gray colors only very close to the surface, because below this gray horizon, you have a horizon that's not fluided, that's not saturated by water, because it have a low porosity and avoid water migration from of the soil profile, from the surface to the subsurface horizon. Okay, so maybe the soil profile that you said that you saw in the field, maybe, I'm not sure, but maybe could be at stagnant soil. You can share with us the photos, the pictures that you take with your soil profile, but maybe is a stagnant soil because the water produce stagnant properties, this iron masses, this plintite, these iron compressions and nodules, and the gray color in a specific horizon that is not affected by water table, but it's induced by a low porosity layer or horizon in the subsurface. Okay? The stagnosols are
Okay.
very common, very common.
Okay, I will check. It was a video.
Oh, very good, very good.
Thank you.
Welcome, welcome. Oh, it's quite common to find in some of these horizons that possess this red color, that some voids register a gray color in the hypocoatings gray colors that we call. It's because the voids, it's always saturated, because the the small voids that we have here and this oxic horizon, it's fulfilled by water. So we start to reduce iron here in the oxic, in this oxic horizon. We start to reduce iron, some spots, some dots of gray horizon, gray areas, but it's very close to the roots, indicating that this gray color is related to the water here that produce the gray color here and start to migrate very slowly through the voids and create this gray features, these reducimorphic features. Okay,
Okay.
so people, now we finish. In the next class, we will talk about the last of the reference soil groups that we need to talk. Okay, we have more 12 reference soil groups to talk about. So it's a large quantity, but I prefer to share them in different classes. So I know that's a lot of information, but could be worse than this, okay? So in the next class, we'll talk about the last 12 reference soil groups that we need to talk. And some of them are very easy to classify, some of them it's not so easy. I think that the worst that are most difficult to find and to classify and to understand are those which I present here in this class. Again, please try to read the material, the reference that I share with you. I think that's the best material to understand how the soils could be classified. I will share with you an additional reference about how these reference soil groups could be used or how they could be formed in the field and the land potential use that could be related to each one, okay? But it's an additional reference that you should read if you have time. But of course, the basic material you all should read. Okay. And again, if you have any question about anything, just send me an email, send me a message, and I will try to answer as soon as possible. Okay.
Okay.
Okay. Okay. All right. So I see you in the next week uh, that we will talk about the last 12 soil reference groups. Okay. So see you. Bye bye.
Bye bye, JJ. Thank you.
Welcome.